There are four conic sections, namely the circle, the ellipse, the parabola, and the hyperbola. We obtain these conic sections when a plane intersects the lateral surface of a right circular cone. Depending on the angle and position of the plane relative to the cone, different types of conic sections result from the intersection of the plane and the cone. We will address this topic in more detail in the subsequent chapters of this video, so stick around. A circle is the set of all points in a plane such that, for any point P in the set, the distance to a fixed point, called the center, is constant. Specifically R, the radius of the circle. Like ellipses, parabolas, and hyperbolas, circles are conic sections, that is, curves obtained by slicing a right circular cone with a plane. Specifically, we obtain a circle when the plane is perpendicular to the axis of rotation of the cone and parallel to its base. The center and the radius are the defining elements of a circle. The center of a circle is a fixed point in a plane around which the circle is constructed. Specifically, all points on the circle are equidistant from the center. This means that any two radii have the same length. The radius is a line segment from the center to any point on the circle. The length of the radius is half the length of the diameter. A diameter is any line segment that passes through the center and has its endpoints on the circle. Its length is twice the length of the radius. A circle has an infinite number of diameters. Each of these diameters is an axis of symmetry that divides the circle into two congruent halves called semicircles. A central angle is an angle whose vertex is the center of a circle and whose sides are two radii. The endpoints of the two radii lie on the circle and determine an arc that subtends the central angle. A chord is a line segment whose endpoints lie on the circle. The longest chord is the diameter of the circle. The sagitta is the height of an arc, i.e., the distance from the midpoint of the arc to the midpoint of its base. Lastly, a secant line is a line that intersects a circle at exactly 2 points. Secant lines always cross the circle, unlike tangent lines, which only touch the circle at 1 point. We can draw infinitely many secant lines that intersect a circle. An external point is a point that lies outside the circle. Given an external point, we can draw only 2 tangent lines to the circle from it. A tangent line is a line that touches a circle at exactly 1 point. Unlike secant lines, tangent lines never cross the circle. We can draw infinitely many tangent lines to a circle. However, from an external point, we can draw only 2 tangent lines to it. A point of contact is a point at which a tangent line touches a circle. The tangent line and the normal line intersect perpendicularly at the point of contact. A normal is a line perpendicular to the tangent line. Lastly, a chord of contact is a chord whose endpoints are 2 points of contact. When we draw 2 tangent lines to a circle from an external point, these tangent lines touch the circle at 2 distinct points. The line segment connecting these 2 points of contact is called the chord of contact. An arc is the distance between 2 points along the circumference of a circle. The 2 points that define the arc are called the endpoints. These points can be any 2 distinct points on the circle. An arc is associated with the angle formed at the circle's center by radii drawn from the center to each of the endpoints. This angle is known as the central angle. The length of the arc is directly related to the measure of this angle and the length of the circle's radius. A sector is a region enclosed by 2 radii of a circle and the arc between them. The 4 quadrants of the circle and the 2 semicircles are special types of sectors. Lastly, a segment is a region enclosed by a chord and the arc between the endpoints of the chord. The circumference of a circle is the distance around the circle, i.e. its length. And the area of a circle is the size of the surface enclosed by the circle. An ellipse is the set of all points in a plane such that, for any point P in the set, the sum of the distances to 2 fixed points, called the foci, is constant, specifically 2a, the length of the major axis of the ellipse. Like circles, parabolas, and hyperbolas, ellipses are conic sections, that is, curves obtained by slicing a right circular cone with a plane. Specifically, we obtain an ellipse when the plane intersects the lateral surface of the cone at an angle to its axis of rotation different from 90 degrees, but doesn't intersect its base. The foci of an ellipse are 2 fixed points in a plane about which the ellipse is constructed. They're usually denoted by F1 and F2 and lie on the major axis of the ellipse, symmetrically on either side of the center. For any point P on the ellipse, the sum of the distances from P to each of the 2 foci is always equal to 2a, where a is the length of the semi-major axis. If the ellipse is oriented horizontally, the coordinates of the 2 foci are -c, 0, and c, 0, respectively, where c is the focal distance. The major axis and the minor axis of an ellipse are its 2 axes of symmetry, which intersect perpendicularly at the center of the ellipse. They define the ellipse's shape and size. For instance, the longer the major axis, the more elongated the ellipse becomes. In an ellipse, the major axis is typically longer than the minor axis. If the major axis and the minor axis are equal in length, the ellipse becomes a circle, and the 2 foci coincide at the center of the circle. The vertices of an ellipse are the 2 points where the ellipse intersects its major axis, reaches its maximum distance from the center, and turns around. If the ellipse is oriented horizontally, the coordinates of the 2 vertices are -a, 0, and a, 0, respectively, where a is the length of the semi-major axis. The co-vertices of an ellipse are the 2 points where the ellipse intersects its minor axis, reaches its minimum distance from the center, and turns around. If the ellipse is oriented horizontally, the coordinates of the 2 co-vertices are 0, b, and 0, -b, respectively, where b is the length of the semi-minor axis. The focal distance is the distance from the center of the ellipse to either of the 2 foci. It provides information about the ellipse's eccentricity. Specifically, the longer the focal distance, the more elongated the ellipse becomes, and conversely, the shorter the focal distance, the less elongated the ellipse becomes. Lastly, the center of an ellipse is the midpoint of both the major axis and the minor axis. It is also the midpoint between the 2 foci. An ellipse can be placed anywhere in the plane, so its center can have any coordinates, hk. However, for simplicity, Ellipses are often positioned with their center at the origin 0, 0 of the Cartesian coordinate system. A chord is a line segment whose endpoints lie on the ellipse. The longest chord is the major axis of the ellipse. Focal chords, the major and minor axes, and the two latus recta of the ellipse are special types of chords. An ellipse can have infinitely many chords. A focal chord is a chord that passes through one of the foci of the ellipse. The two latus recta of the ellipse are special types of focal chords. An ellipse can have infinitely many focal chords. The latus rectum is a chord that passes through one of the foci and is perpendicular to the major axis. Because there are two foci, there are also two latus recta in total, one on the left side of the ellipse and one on the right side. Lastly, a secant line is a line that intersects an ellipse at exactly 2 points. Secant lines always cross the ellipse, unlike tangent lines, which only touch the ellipse at 1 point. We can draw infinitely many secant lines that intersect an ellipse. An external point is a point that lies outside the ellipse. Given an external point, we can draw only 2 tangent lines to the ellipse from it. A tangent line is a line that touches an ellipse at exactly 1 point. Unlike secant lines, tangent lines never cross the ellipse. We can draw infinitely many tangent lines to an ellipse. However, from an external point, we can draw only 2 tangent lines to it. A point of contact is a point at which the tangent line touches the ellipse. The tangent line and the normal line intersect perpendicularly at the point of contact. A normal is a line perpendicular to the tangent line. Lastly, a chord of contact is a chord whose endpoints are 2 points of contact. When we draw 2 tangent lines to an ellipse from an external point, these tangent lines touch the ellipse at 2 distinct points. The line segment connecting these 2 points of contact is called the chord of contact. The directrices of an ellipse are 2 fixed lines in the plane, located outside the ellipse, that are used in the construction and definition of the ellipse. If the directrices are vertical, the ellipse stretches horizontally, whereas if the directrices are horizontal, the ellipse stretches vertically. An ellipse can also be defined as the set of all points in a plane such that, for any point P in the set, the ratio of the distance to a focus to the distance to the corresponding directrix is constant, and this ratio is equal to the eccentricity E of the ellipse. This ratio is always less than 1 for an ellipse. The circumference of an ellipse is the distance around the ellipse, i.e., its length. The most precise way to calculate the circumference of an ellipse involves the complete elliptic integral of the second kind. To find the circumference, we first calculate the arc length of the first quarter of the ellipse, and then multiply this value by 4 to obtain the total circumference. And the area of an ellipse is the size of the surface enclosed by the ellipse. To calculate the area of an ellipse, we use the formula A equals pi times A times B, where A is the semi-major axis and B is the semi-minor axis. Since an ellipse can be thought of as an elongated circle, this formula can be derived from the area formula of a circle. Specifically, if we start with a circle of radius B and stretch it by a factor of A in the x direction and by a factor of B in the y direction, we obtain an ellipse. Thus, the area of the ellipse is A equals pi times b squared, all multiplied by A over b, which simplifies to pi times A times b. A parabola is the set of all points in a plane such that, for any point P in the set, the distance to a fixed point, called the focus, is equal to the distance to a fixed line, called the directrix. Like circles, ellipses, and hyperbolas, parabolas are conic sections, that is, curves obtained by slicing a right circular cone with a plane. Specifically, we obtain a parabola when the plane is parallel to exactly one generatrix line of the lateral surface of the cone and intersects its base. The focus of a parabola is a fixed point in the plane around which the parabola is constructed. The closer the focus is to the vertex, the narrower the opening of the parabola. Conversely, the farther the focus is from the vertex, the wider the opening of the parabola. Parabolas have only one focus, unlike ellipses and hyperbolas, which have two foci, and unlike circles, which have no foci. The directrix of a parabola is a fixed line in the plane used to construct the parabola. It determines the shape and orientation of the parabola. Specifically, the closer the directrix is to the vertex, the narrower the opening of the parabola. Conversely, the farther the directrix is from the vertex, the wider the opening of the parabola. The directrix can determine the shape of the parabola because the distance from the vertex to the directrix is equal to the focal length, which is the distance from the vertex to the focus. What's more, if the directrix is horizontal, the parabola opens upwards or downwards, whereas if the directrix is vertical, the parabola opens to the right or to the left. Parabolas have only one directrix, unlike ellipses and hyperbolas, which have two directrices, and unlike circles, which have no directrices. The vertex of a parabola is the point on the parabola at which the parabola turns around. It lies halfway between the focus and the directrix. It is the point on the parabola closest to the focus and the directrix. Parabolas have only one vertex, unlike ellipses and hyperbolas, which have two vertices, and unlike circles, which have infinitely many vertices. The axis of symmetry of a parabola is a line that splits the parabola into two congruent halves called arms. It passes through the focus and the vertex and perpendicularly intersects the directrix. Parabolas have only one axis of symmetry, unlike ellipses and hyperbolas, which have two axes of symmetry, and unlike circles, which have infinitely many axes of symmetry. Lastly, the focal length is the distance between the vertex and the focus. It determines the shape of the parabola. Specifically, the shorter the focal length, the narrower the opening of the parabola. Conversely, the longer the focal length, the wider the opening of the parabola. A chord is a line segment whose endpoints lie on the parabola. Focal chords and the latus rectum of the parabola are special types of chords. A parabola can have infinitely many chords. A focal chord is a chord which passes through the focus. The latus rectum of the parabola is a special type of focal chord. A parabola can have infinitely many focal chords. The latus rectum of a parabola is a chord that passes through the focus, is parallel to the directrix, and perpendicularly intersects the axis of symmetry. It is a measure of the opening of the parabola. Specifically, the shorter the latus rectum, the narrower the opening of the parabola. Conversely, the longer the latus rectum, the wider the opening of the parabola. The length of the latus rectum is 4 times the focal length. Lastly, a secant line is a line that intersects the parabola at exactly 2 points. Secant lines always cross the parabola, unlike tangent lines, which only touch the parabola at 1 point. We can draw infinitely many secant lines that intersect a parabola. An external point is a point that lies outside the parabola. Given an external point, we can draw only 2 tangent lines to the parabola from it. A tangent line is a line that touches the parabola at exactly 1 point. Unlike secant lines, tangent lines never cross the parabola. We can draw infinitely many tangent lines to a parabola. However, from an external point, we can draw only 2 tangent lines to the parabola. A point of contact is a point at which the tangent line touches the parabola. The tangent line and the normal line intersect perpendicularly at the point of contact. A normal is a line perpendicular to the tangent line. Lastly, a chord of contact is a chord whose endpoints are 2 points of contact. When we draw 2 tangent lines to a parabola from an external point, these tangent lines touch the parabola at 2 distinct points. The line segment connecting these 2 points of contact is called the chord of contact. The axis of symmetry of a parabola is a line that splits the parabola into 2 congruent halves, called arms, which are mirror images of each other. The 2 arms start at the vertex and extend away from it in opposite directions infinitely, never meeting again after they separate at the vertex. A hyperbola is the set of all points in a plane such that, for any point P in the set, the absolute value of the difference of the distances to 2 fixed points, called the foci, is constant, specifically 2a, the length of the transverse axis of the hyperbola. Like circles, ellipses, and parabolas, hyperbolas are conic sections. In other words, curves obtained by slicing a right circular cone with a plane. Specifically, we obtain a hyperbola when the plane is parallel to the axis of rotation of the double cone and perpendicularly intersects its 2 bases. The foci of a hyperbola are 2 fixed points in the plane around which the hyperbola is constructed. The closer the foci are to the vertices, the narrower the opening of the 2 branches of the hyperbola. Conversely, the farther the foci are from the vertices, the wider the opening of the 2 branches of the hyperbola and the straighter the 2 branches. Hyperbolas and ellipses have 2 foci, unlike parabolas, which have only 1 focus, and unlike circles, which have no foci. The transverse axis and the conjugate axis of a hyperbola are its 2 axes of symmetry, which intersect perpendicularly at the center of the hyperbola. They define the shape and size of the hyperbola. For instance, the longer the transverse axis, the farther apart the 2 branches become. In a hyperbola, the transverse axis can be longer than, shorter than, or equal to the conjugate axis. The longer the transverse axis is compared to the conjugate axis, the narrower the opening of the two branches of the hyperbola. Conversely, the shorter the transverse axis is compared to the conjugate axis, the wider the opening of the two branches of the hyperbola, and the straighter the two branches. If the transverse axis and the conjugate axis are equal in length, the hyperbola becomes a rectangular hyperbola, and its two asymptotes are perpendicular. The vertices of a hyperbola are the 2 points at which the hyperbola intersects its transverse axis, reaches its minimum distance from the center, and turns around. If the hyperbola opens horizontally, as is the case in this diagram, the coordinates of the two vertices are negative a, 0, and a, 0, respectively, where a is the length of the semi-transverse axis. The two vertices of a hyperbola are the endpoints of its transverse axis. Thus, the distance between the two vertices is equal to the length of the transverse axis, which is 2a. The endpoints of the conjugate axis don't lie on the hyperbola. The conjugate axis never intersects the hyperbola. As a result, hyperbolas have no co-vertices, unlike ellipses, which have two co-vertices because their minor axis intersects them. The focal distance is the distance from the center of the hyperbola to either of the two foci. It provides information about the hyperbola's eccentricity. Specifically, the longer the focal distance, the wider the opening of the two branches of the hyperbola. Conversely, the shorter the focal distance, the narrower the opening of the two branches. To calculate the focal distance, we use the semi-transverse axis and the semi-conjugate axis of the hyperbola. Specifically, the focal distance is equal to the square root of a squared plus b squared. The central rectangle of a hyperbola is determined by the transverse and conjugate axes of the hyperbola. Specifically, one pair of opposite sides is parallel to and equal in length to the transverse axis, whereas the other pair of opposite sides is parallel to and equal in length to the conjugate axis. The asymptotes of the hyperbola contain the diagonals of the central rectangle and pass through its vertices. For this reason, if we want to graph the asymptotes of the hyperbola, we only have to extend the diagonals of the central rectangle. The asymptotes of a hyperbola are two straight lines that intersect at the center of the hyperbola. Each of the two asymptotes is approached by diagonally opposite arms. As the arms of each branch extend infinitely, the distance between the arms and the asymptotes approaches 0. In other words, as they extend, the arms of each branch get increasingly closer to the asymptotes, but never meet them. Lastly, the center of a hyperbola is the midpoint of both the transverse axis and the conjugate axis. It is also the midpoint between the two foci. A hyperbola can be placed anywhere in the plane, so its center can have any coordinates, h, k. However, for simplicity, hyperbolas are often positioned with their center at the origin 0, 0 of the Cartesian coordinate system. A hyperbola is symmetric with respect to its center, meaning that the two branches are mirror images of each other. A chord is a line segment whose endpoints lie on the hyperbola. Focal chords, the transverse axis, and the two latus recta of the hyperbola are special types of chords. In a hyperbola, some chords connect 2 points on the same branch of the hyperbola, whereas other chords connect 2 points on opposite branches. A hyperbola can have infinitely many chords. A focal chord is a chord that passes through one of the foci of the hyperbola. The two latus recta of the hyperbola are special types of focal chords. A hyperbola can have infinitely many focal chords. The latus rectum is a chord that passes through one of the foci and is perpendicular to the transverse axis. Because there are two foci, there are also two latus recta in total, one within the left-hand branch of the hyperbola and one within the right-hand branch of the hyperbola. To calculate the length of the latus rectum, we use the semi-transverse and semi-conjugate axes of the hyperbola. Specifically, the length of the latus rectum is equal to 2 times b squared, all divided by a. This formula shows that the longer the transverse axis, the shorter the latus rectum becomes. Conversely, the shorter the transverse axis, the longer the latus rectum becomes. Lastly, a secant line is a line that intersects a hyperbola at exactly 2 points. Secant lines always cross the hyperbola, unlike tangent lines, which only touch the hyperbola at 1 point. In a hyperbola, some secant lines cross only one branch, whereas other secant lines cross both branches. We can draw infinitely many secant lines that intersect a hyperbola. An external point is a point that lies outside the hyperbola. Given an external point, we can draw only 2 tangent lines to the hyperbola from it. A tangent line is a line that touches a hyperbola at exactly 1 point. Unlike secant lines, tangent lines never cross the hyperbola. We can draw infinitely many tangent lines to a hyperbola. However, from an external point, we can draw only 2 tangent lines to it. A point of contact is a point at which the tangent line touches the hyperbola. The tangent line and the normal line intersect perpendicularly at the point of contact. A normal is a line perpendicular to the tangent line. Lastly, a chord of contact is a chord whose endpoints are 2 points of contact. When we draw 2 tangent lines to a hyperbola from an external point, these tangent lines touch the hyperbola at 2 distinct points. The line segment connecting these 2 points of contact is called the chord of contact. The directrices of a hyperbola are 2 fixed lines in the plane, located outside the hyperbola, that are used in the construction and definition of the hyperbola. If the directrices are vertical, the hyperbola opens horizontally, whereas if the directrices are horizontal, the hyperbola opens vertically. The distance from the center to either of the directrices is equal to a squared divided by c, where a is the length of the semi-transverse axis and c is the focal distance. This formula shows that the longer the focal distance, the shorter the distance from the center to either directrix becomes. Conversely, the shorter the focal distance, the longer the distance from the center to either directrix becomes. A hyperbola can also be defined as the set of all points in a plane such that, for any point P in the set, the ratio of the distance to a focus to the distance to the corresponding directrix is constant, and this ratio is equal to the eccentricity E of the hyperbola. This ratio is always greater than 1 for a hyperbola. A hyperbola has 2 branches that are mirror images of each other. Each branch is divided into 2 congruent halves, called arms, by the transverse axis. These arms start at the vertices and extend infinitely in opposite directions, never meeting again. This infinite extension of the arms in opposite directions is what makes hyperbolas open and unbounded curves. Like, share, and leave a comment. Thank you for watching, and don't forget to subscribe to my YouTube channel.